Let's look at another iterated integral. In this particular case, we can go ahead and write down what the integration region is, R. We see that the outer integral is the x variable, so x runs from 0 to 4, so that's the independent variable, and then the inner integral corresponds to y, so y runs from x to 4, as we've written here. So we're asked to switch the order of integration, but let's just notice why this would be something good to do. If we have to do the y integration first, this would be a very difficult antiderivative. And so what we want to do is hopefully switch the order of integration and make the antiderivative much easier. So let's just go ahead and do that. Now this is a little bit simpler algebraically, but it's always good to look at a problem that's easy and practice your techniques. So now when we look at this region of integration, notice here that the smallest x can be is 0. So this automatically gives us that y will run between 0 and 4. So we get this basically by observation. Now what's going on with the x? Well, from the bottom inequality, we see that x is greater than or equal to 0. And then from the top inequality, we see that x is less than or equal to y. And now if we can combine those, which we can easily do, we see that x is between 0 and y, lower limit, upper limit. So the switching of the integration order was very simple with this problem. And so now we can write y running from 0 to 4 as the independent variable, and then x running from 0 to y as the dependent variable. And so now we take our original integral I and we write it with the new order. And so again, the integrand looks the same, but now the order of integration has been switched. So first what we want to do is an x integration. So again, this term here relative to x is constant, so we don't do anything with it. So we add 1 divided by the new power, so we get x squared over 2. And then of course this is constant relative to the x variable. Now we can go ahead and evaluate. We replace x with y to get a y squared over 2, and then of course when we replace x with 0, we just get 0. So what we can do now is factor the 1/2 here. And notice the y squared is almost what we need, but when we look at the chain rule here, when we take the derivative of 1 plus y cubed, we get a 3y squared. And so we need a 3. So to make this table ready, we put the 3 in here and then counter it out here to pay for that 3. So as I've written here, this is now table ready. But this is a very simple integral because we have the u and we have the du. So we can go ahead and add 1 divided by the new power. So here we add 1 to 1/2 and we get 3/2. And division by 3/2 would be multiplication by 2/3. And I went ahead and left this factored, so now we see the 2's absorbed and the 3's multiply to give us a 1/9. And now at this point, we can easily finish the problem just by again applying the fundamental theorem of calculus. We're going to replace y with a 4 and replace y with a 0. And in doing that, we get a 1 plus 64 to the 3/2 power and a 1 plus 0 to the 3/2 power. So simplifying, this will give us 1/9 times the quantity, the 3/2 power of 65 minus 1. And we are done.